Okay, I think it's already time to start the lecture.
Correct.
So I welcome everybody on our 7th lecture of astrochemistry lecture course. This lecture will be given by Professor Rens Waters from Radboud University and through Netherlands Institute for Space Research. He will speak about astrochemical observation with a focus on the instrumentation. So please, Rens, the floor is yours.
Yeah, thank you very much. And good afternoon, everybody, or good day after everybody. Not sure what time zone you are, but it's a pleasure to be able to present this lecture in this very nice series on astrochemistry. And as you can see, the title of my talk is Instruments, but I will actually be talking about two topics. I will discuss a bit what kind of telescopes and instruments we're using for the study of interstellar matter and circumstellar matter, but I'll also talk about solids in space and solids around stars, in particular planet-forming disks. So the outline of my talk, I hope that this is visible. Can somebody really tell me if you can see the next slide?
No.
You don't see my next slide. All right, okay. That is interesting. Because this was tested just before we started. Excuse me, everybody. This is a bit of a... Let's try this again.
Yes.
Can you see my screen now?
Yes. Yes.
Right. So, apologies. So this is an overview of today's lecture. I'll start, of course, with an introduction. Then I'll go a bit into what Ted Bergen talked about last week, diagnostics of gas. And then I'll discuss telescopes, the spectroscopy and the imaging that we want to do with those telescopes, and just go through a bit of the basics of that. And then I'll highlight two telescopes that I think are very important for astrochemistry, and those are ALMA and the James Webb Space Telescope. And then I'll dive into solids in space, and that will be a topic that I may have to cut off because of time. But let's see how far we get with that. Okay, so let's dive into the heart of the matter. And I think this is the basic topic of this entire course, trying to understand the cycle of matter in galaxies. And of course, our galaxy being the nearest one is the one that is best studied, where stars evolve, they get born, they live for a while, they eject matter at the end of their lives, and this matter is then given back into the interstellar medium, where it mixes with pre-existing material, then enriched, of course, in nuclear burning products. And so this whole process of star formation starts all over again. And one of the goals of astrochemistry is to try to understand this whole process from the point of view of the chemistry that is taking place in these various different places. And one of the challenges is that there is an enormous range in temperatures and densities that we would like to study. And this is captured in this diagram, where you see on the horizontal axis the density in particles per cubic centimeter, on the vertical axis the temperature in Kelvin. And you can see from the logarithmic scale of this diagram that there's an enormous span in densities and temperatures that are prevalent in interstellar gas and circumstellar gas and dust. From the very tenuous coronal gas that we see in shocked material in our galaxy and other galaxies, all the way into the very dense regions of molecular clouds, where molecules are being formed and stars and planetary systems are being formed. And so we would like to have diagnostics of all these different regions, and we would like to know, well, what are the temperatures of this gas? What are the column densities? What are the densities? What are the abundances of different chemical elements or different molecules? What is the spatial distribution? What is the kinematics if you talk about gas lines, gas species? And what is the mass and composition of the solids? So many questions to be addressed. And obviously, because we're astronomers, what we do is we use telescopes and instruments behind those telescopes to measure these quantities. And here you see a a collection of those. Of course, there are many different telescopes in many different spectral ranges that people have developed, but here are just a few that are actually ground-based, and that you can see from the fact that there's not one telescope, but there are more than one telescope in every picture. So that means that they can also be combined as interferometers, and we will get to interferometry in a moment. But here you see the very large telescope, the VLT in Chile. You see the very large array in the US. You see the small, the SMA array on the top of Mauna Kea on Hawaii, and you see the ALMA millimeter array in Chile. And so all these different telescopes have their specialties in observing and getting our hands on the quantities that were on the previous slide. And of course, if you want to spatially resolve those objects, then it depends very much on where they are. And here you can see a diagram where you see the physical scale of objects on the vertical axis. So we go from the solar system to planet-forming disks, to star clusters, to star-forming regions on the vertical axis, and their scales go from 1 astronomical unit to kiloparsec scales. And on the vertical axis, on the horizontal axis, you see the distance at which you can place those objects, starting from very close by on parsec scale all the way to cosmological distances. And these vertical lines tell us what is the angle scale that these telescopes can reach for those different objects at a various distance. So that means, for instance, that a planet-forming disk can be resolved with telescopes like the Hubble Space Telescope, the James Webb Space Telescope, but also the one which is on the drawing board, which is a successor to the James Webb Space Telescope. And this diagram is called HDST. This is a bit of an older diagram, but now it's called the Habitable Worlds Observatory, which would have a telescope with a diameter of the order of 10 meters. And those telescopes have a limited spatial resolution. We will get to that. And you can see here that the different objects can only be spatially resolved out to a certain distance for a certain telescope diameter. So the choice of telescopes and the diameter of the telescopes sets a strong limit on how far we can see, to what distance we can actually spatially resolve different objects. And in this game, of course, bigger is better. So bigger telescopes help to see fainter things and also to resolve objects more and better. Here you see this is another way to say this as a function of wavelength in micrometers. So we have here the ultraviolet, here the near-infrared, the mid-infrared, the thermal infrared, and then here we go into the ALMA wavelength regime. And on the vertical axis, you have the angular resolution in arcsecond of telescopes, and every line in this diagram is a specific telescope. For instance, here, the ALMA telescope, just as an interferometer, you can see that at the bottom of this diagram, has a very high spatial resolution because it is an interferometer, and we'll see how this is achieved in a moment. And here's an example again of the James Webb Space Telescope, which is a single dish telescope, which has an angular resolution typically of the order of, well, less than a tenth of an arcsecond at the shortest wavelengths, and then increasing up to a few tenths of an arcsecond at the longest wavelengths where Webb is operational. And here are a few other telescopes that have been around, like the Herschel millimeter telescope of the European Space Agency, and Sophia, which was an aircraft which had an infrared telescope. And so picking your telescope and getting there and knowing the aperture can then translates into a certain angular resolution with which you can resolve different objects. If you then go and zoom into particular objects, and this is one of the favorite objects that I will be talking about, so I'll be using planet-forming disks a lot as an example. Here you have an artist impression of the physical structure of a planet-forming disk, with a star in the middle and a gaseous rotating Keplerian or semi-Keplerian disk of gas and dust surrounding it. And you can see the spatial scale of these different components. So we start at scales of typically 0.1 of an astronomical unit in this case, and then we go to typical scales of few tenths or a few hundred of astronomical units. And if you want to observe and spatial resolve that, that means that you, and here's an example of such a disk, but then resolved with the ALMA telescope, an ALMA image, where you see what we actually physically, what we see on the sky of such an object. And you here have the angular scale in arcsecond. So you really need sub-arcsecond angular resolution in order to start seeing details in a planet-forming disk. And even to zoom in to the inner parts of planet-forming disks. If you want to do that spatially resolved, then you need angular resolutions for the nearby star-forming region. So typically at a distance of 150 to 200 parsecs of a few tenths of milliarcseconds, or even to the milliarcsecond level. And so that's a very large challenge in order to reach that. If you want to observe planets around stars, here's an example of how this can be done, but done with the coronagraph. So what's happened here, and this is a very famous example of a very bright nearby star, HR 8799, which has 4 gas giant planets orbiting in very wide orbits, but the star is an A-type star, it's very bright, and it would completely outshine all the planets that are orbiting it. And so what has been done here is made use of a coronagraph, which is a technique that is used a lot to cover up the central star of a bright object, and then you can observe a lot more fainter objects that are in this close vicinity. And so this coronagraphic technique is used a lot for instance, direct imaging of disks, where you can then probe typically to distances for the disks that are at 150 to 200 parsecs of the order of a few tenths of astronomical units, to give you an idea. Of course, we also want to have information about the kinematics of gas in, for instance, planet-forming disks. And so here's an example of what kind of kinematics, what kind of velocities you can expect in such objects. And so we have the outer disk to start out with, for instance. So assuming that these disks are rotating in a Keplerian motion, these outer disks have and disk winds have typically velocities of the order of 1 to a few kilometers per second. But in the inner disk, of course, the rotation is much faster. At an orbit of an astronomical unit, you can imagine that for a solar-type star, the rotational velocities are of the order of 30 kilometers per second. So typically, if you want to spectrally resolve kinematics of gases in the inner disks, you need 10 to 100 kilometers per second. And they're not drawn in this diagram, but present in many young objects that are still accreting are jets and collimated outflows, and those have typically velocities of several hundred kilometers per second. So depending on what kind of parts of such a disk you want to study, you need spectral resolutions that are very high, of the order of kilometers per second or more, but sometimes you can also do with modest spectral resolution if you want to study things that move very fast. That is a first introduction to what we want to achieve and the telescopes we have and the instruments behind it. Let's now do a quick recap of some of the material that Ted Birkin discussed last week, because we want to study different phases of interstellar gas, both atomic and molecular gas at different temperatures and pressures. We use different diagnostics, different transitions that probe different regimes in density and temperature. And here's a summary of typically the probes that we have and what kind of wavelengths they are. So forbidden lines with low Einstein A coefficients are typically found at optical wavelengths. Fine structure lines of atoms and ions are found in the infrared spectral region. Electronic transitions of molecules are found in the UV or at optical wavelengths. But the vibrational and the rotational lines are typically found at infrared and all the way into the radio regimes. And obviously, because of this enormous difference in wavelengths, there's no single telescope or single receiver that is able to detect and characterize all these different transitions. So you need to pick your telescope and your instrument in order to study the kind of environment that you're interested in. And for the atomic lines and for the fine structure lines, there is an enormous range of parameter space that we can have access to. And this is depicted in this diagram where we have on the horizontal axis the excitation potential of a particular transition of an atom or an ion, and if it's in certain environments. And on the vertical axis, we have the critical density in units of per cubic centimeter. And to remind everybody from last week's lecture, the critical density is defined as the ratio between the Einstein A coefficient and the collisional cross-section Q. And simply this means that if you have a gas with a certain density, the critical density tells you at what kind of density those lines are particularly well excited by collisions, and where the time scale between collisions is short enough, is long enough that a photon can, that an atom can, or an ion can spontaneous decay and emit a photon. And so you can see here that that these lines probe an enormous range in density, 7 orders of magnitude, but they also probe an enormous range in excitation potential. So that means that we have access to lines that probe very hot coronal gas. For instance, up here in this diagram, you see a very high ionizations of, for instance, iron or silicon. But also you can go down here and probe very low density gas that's neutral or singly ionized. Then if we switch to molecules, as you saw last week, molecules can have vibrational, electronic vibrational and rotational transitions. And this is depicted in this diagram where you see here a potential well of a molecule that can go from the ground electronic state to an excited electronic state. And within those electronic states, the molecules can have both vibrational energy levels and rotational energy levels. And especially in the infrared, of course, we are sensitive to these rotational and at millimeter and longer wavelengths, I should also say, we are sensitive to both the the vibrational and the rotational transitions. Here's an overview of important rotational vibrational bands in the infrared, zooming into the 3 to 30 micron spectral range, where you can see for different groups of molecules where at what particular wavelength, or if you're more interested in frequency, the frequency scale is down here. You can find important vibrational stretches. So the upper part gives the stretching vibrational resonances, at what wavelengths you can find them. And here you can see a few of the important bending frequencies of particular molecules. And so this is a very rich spectral range where you can study these vibrational resonances, both in the gas phase but also in the solids. Remember that molecules can be both in the gas phase and in the solid phase. And in the gas phase they can show both rotation and vibration, but in the solid phase they can only show vibrations. And those vibrational bands are then obviously at roughly the same wavelengths that we see in the gas phase, but in the solid phase they're often slightly shifted. And then for molecules, you can make a similar diagram as for the atomic and the ionic lines, but then in just a slightly different notation of the axis. So on the horizontal axis here, we have the kinetic temperature of the gas in Kelvin, and on the vertical axis, we have the molecular hydrogen density in particles per cubic centimeter. And you can see here that for different molecules like carbon monoxide, or light hydride molecules, there's a range in temperatures and densities that these particular transitions probe. Again, because like with the atoms and the ions, Also molecule and molecular transitions can be characterized by critical densities in which the Einstein A coefficient and the collisional rates are related like this. And for molecules, the Einstein A coefficient goes proportional to the electric dipole moment in squared and to frequency to the third power. So that means that the critical densities increase, and generally speaking, with wavelengths, with frequency. And you can see that, for instance, for CO, this bar goes up here to higher, so higher densities and higher temperatures. And these different molecules probe very different temperatures sometimes, and because of their internal energy level structure. For instance, here's an example where molecular hydrogen and CO are compared, where you can see very closely packed and very low-lying energies of carbon monoxide. These are all pure rotational lines. And here we have molecular hydrogen. Because of the lower weight of the molecule, of hydrogen atoms in the molecule, the reduced mass of the molecule is lower, and therefore these rotational levels are at much higher frequencies. And it also means that, for instance, molecular hydrogen probes a much warmer gas than the CO gas at the lowest lying level. So H2 transitions are not sensitive to very cold gas, unfortunately, but carbon monoxide gas is, and that's why often people use CO to probe cold molecular gas, and then they use some kind of magic conversion from CO abundance to total abundance by assuming a certain abundance of CO versus H2 molecules. Okay, so far for a brief recap of what Ted Bergen talked about last week, and of course now we want to observe all of this spectral diagnostics with telescopes, and ideally, if you point the telescope at the sky, you would like to have an instrument that provides you with very high spectral resolution and very high spatial resolution, and you can study your object in as much detail as you want. But of course, such telescopes only exists on the drawing board, and we need to use different telescopes with different approaches to either, for instance, you go for high spectral resolution or to go for high spatial resolution, and so pick the instruments and the telescopes to answer your scientific questions. So let's look now a bit at spectroscopy and what kind of basic concepts people have employed to get to spectrally resolve transitions of atoms and ions and molecules from interstellar gas and dust, from interstellar gas. And here's a very simple diagram. So we define the spectral resolution simply as the wavelength at which we observe it by the resolving power. So the resolving power is defined by the ratio of the wavelength over the wavelength resolution that we have. So the two wavelength units that we can still separate in the spectrograph from each other. There are, of course, many different instruments with many different solutions to get to a spectrum. I thought it was probably better to give you an overview of this very conceptually rather than to go into very detailed descriptions of instruments one by one, because that also gets very boring very quickly. But so here is an overview of what many different instruments offer. They either use a prism, which gives you a modest spectral resolution, and the principle behind that is wavelength-dependent refractive index of the material of which the prism is made of. Then we have gratings, and a picture of a grating is given here in this diagram here. These gratings give intermediate spectral resolution, and the principle is wavelength-dependent diffraction of the incoming wave as it interferes, as it's being reflected. The interference pattern becomes wavelength-dependent, and this is a way where you separate the different rays in different wavelengths. And then for very high spectral resolution, there's a technique called heterodyne spectroscopy, where you actually mix in the signal that you want to detect with a different signal, and that causes an interference signal, which is at a much lower frequency than the signal you want to observe, than the signal you want to observe, and therefore is more easily detectable. And so that offers spectral resolutions typically of the order of much better than a kilometer per second. And so that's very interesting if you, for instance, have cold gas like we saw in a planet-forming disk, where we really need, if we want to resolve the kinematics of that gas in outer disks, where we need spectral resolutions better than a kilometer per second. And gratings are typically providing spectral resolutions in the order of a few hundred to a few thousand, or even a few tens of thousands if you have a very high quality grating. And prisms typically give a spectral resolution of 100 to a few hundred. And so all of these different principles are being used in different telescopes at different wavelengths, with different techniques and ways in which these instruments are being designed, have been designed in order to provide spectral resolution that you need in order to observe and detect and resolve spectrally these different transitions. And here's an example of a heterodyne receiver, which is the hi-fi instrument on board of the Herschel Space Observatory. And Ted Bergen actually was leading one of the programs on the Herschel Observatory. And you can see here an enormous forest of different rotational emission lines of molecules in the Orion molecular cloud. And of course, this is a great hunting ground for astrochemistry, because it gives you a lot of detailed information about what kind of molecules there are there, but also by for instance, constructing rotational diagrams, also getting information about the abundances of those molecules, the temperatures of those molecules, and because of the high spectral resolution, also get information about the kinematics of the gas in such environments. Here's an example of a grating spectrograph, which is the MIRI instrument on board of the James Webb Space Telescope. And this is an example of a planet-forming disk that has been observed in a massive star-forming region, and all the peaks you see here are due to, at the top diagram here, are due to rotational, rho vibrational emission of the CO molecule in the V equals 1 to 0 vibrational band. And so every peak is a rotational line in that vibrational band. And mixed in is also a few water lines in this spectral region. And below here is the same, but then a different spectral range for the same object, where some bands of HCN, C2H2, and CO2 are being detected. So it's an example of what you can reach with the grating spectrographs on board of Webb. And then, as Ted Bergen was explaining last week, if you have many of those transitions, and this is an example of carbon monoxide, you can make so-called rotation diagrams in which you plot the line strength, or the line strength divided by the statistical weight versus the energy of the upper level of a particular transition. And all these different dots are observations, in this case, of the V equals 1 to 0 and the V equals 2 to 1 vibrational bands of carbon monoxide. And by measuring the slopes of these lines, you can actually derive the temperature, that is the excitation temperature of the gas. And of course, the amount of emission is proportional and depends on how many CO molecules you have and on their emitting surface, depending on whether it's optically thin or optically thick emission. And then if you have an idea about what object you're looking at, in this case, we have that because we know it's a planet-forming disk. So you can then translate these values like temperatures and surfaces to where you are in the planet-forming disk. And in this case, these temperatures are very high. There might actually be some non-local thermal dynamic equilibrium effects in this, so you have to be careful to to explain these temperatures in terms of kinetic temperatures, but we still think that this CO gas must be very close to this to the central star, and so we know that we can place this CO emission in this innermost region at distances of less than 1 astronomical unit. So this is a sort of a poor man's way, if you have an idea about what object you're looking at, to translate spectral information into spatial information. And here's another example where you can do that, where you have even higher spectral resolution, and this is a spectral resolution of many tens of thousands. I think it's about 35,000, where again the CO molecule has been observed in again a planet-forming disk, just to stick to the same type of object. And what you can see here is this double peak, which is typically the signature of a rotating Keplerian disk. But in fact, in this case, you see two peaks measured in the different rho vibrational bands. The vehicles 2 to 0, that is at 2.32 microns of CO, probes very hot gas. You can see one ring there of gas, and then the other lines of CO probe a lower temp probe, a rotating ring of CO gas at a lower velocity because the peaks are closer together. And so then you can interpret this as a disk with actually two rings of CO gas located typically here at a few tenths of an astronomical unit, and then the second one at 1 astronomical unit. So this is another example, and that's the reason why I show this, and there are many more in the literature where you can use very high spectral resolution to infer something about the geometry of the object you're looking at. So in that sense, this is again a way to use spectroscopy to get an idea about geometry. But of course, yes. So that's all I wanted to say about spectroscopy of different instruments and the way we do this. Then one important question I thought was important to address is the question of why we go and pay so much money and do so much effort and to go to a place where things are very hostile, which is into space. Or why do we need space telescopes to observe some of the regions that we're interested in interstellar space or in circumstellar environments? And the picture you see here actually is the last stage of is actually the James Webb Space Telescope, as it had just separated from the last stage of the Ariane 5. Excuse me for the typo in this slide. The last stage of the Ariane 5 rocket. Webb was launched Christmas Day of 2021. Of course, one of it's the largest telescope ever put in space, and it's producing fantastic new science, as you I'm sure have seen. There are two very important reasons why we want to go to space, and one of them is that the Earth's atmosphere is not transparent at all frequencies, and so that means that a certain emission, and that particularly holds for X-rays and gamma rays. The Earth's atmosphere is just not transparent, and you can see that on this diagram, where on the horizontal axis we have the wavelength of radiation in nanometers, and on the vertical axis we have the Earth's atmospheric capacity, and 100% means that no radiation reaches the surface of the Earth, and 0 means that everything reaches the surface. And you can see here that from the near of UV all the way to gamma rays, the Earth's atmosphere is not transparent. In the optical, of course, it is. And then in the infrared, it's sort of okay, but not great. You can see that there are many different absorption regions, absorptions, because of obviously the molecules in the Earth's atmospheres like water and CO2. Which makes it basically hopeless again in the far infrared and the millimeter. And then as you go to radio wavelengths, it gets better again until it becomes opaque again. And so this is why specifically for X-rays and gamma rays, space astronomy has been developed and is very important, but also for infrared astronomy, space observations have been crucial in order to open large parts of the electromagnetic spectrum. But there's another reason why space is so important, and that is because of the amazing stability that it offers. If you put the telescope in, for instance, one of the Lagrangian points, then the environment is so stable that you can reach very high accuracy in measuring the brightnesses, for instance, as a function of time, and so do things like astroseismology and do very accurate transit observations of exoplanets. And here's an example that I couldn't resist showing you, where you see the spectrally resolved transit of a Saturn mass hot gas giant planet, WASP 39b, which orbits a star in an orbital period of a few days. And what you can see here is the transit light curve. So here the planet is not in front of the star, but then suddenly it passes in front of the star, so it takes away some energy, some radiation, because the planet is cold and the star is warmer, and then it moves away from the star again, and then we're out of this transit. And you can see, so this little movie was put on the web by one of the members of the ERS team, early release science team of James Webb Space Telescope, and I've drawn this red line to guide the eye, because what you see here with your bare eyes is how the planet's size changes as you change wavelength. So in the signature of carbon dioxide, which is this peak here in the spectrum, the planet is just a bit larger than when you observe at frequencies or wavelengths outside of that CO2 band. And so you can actually see with your bare eyes that the planet gets a bit bigger. There it is, there's the CO2, and then it gets noisy. So now we're not in the CO2 band, and then suddenly, there it is. Yep, there it is. You can see the planet going a bit bigger. That you can see this in a movie directly by just plotting the light curve as a function of wavelength is absolutely amazing. And so that gives you a very important other reason why we go to space, because of the amazing accuracy of the signals that we have. And here's an example of many telescopes that have been around. Some of them are still going strong, like James Webb and the Hubble Space Telescope, obviously. And here are a few of the predecessors of Webb. The infrared astronomical satellite that was operational in 1983, that opened up and made the first all-sky survey. The Infrared Space Observatory from the European Space Agency that operated in the mid-90s, and the Spitzer Space Telescope of NASA that operated from 2003 onwards, and the cold mission ended in 2009. And then it went on for a few more years to observe in the near-infrared, and then the Herschel Space Observatory from the European Space Agency that was launched in 2009 and operated until 2013, and observed the sky and at sub-millimeter and millimeter wavelength ranges. So all of those telescopes have been enormously successful and have brought us a lot of new information about astrochemistry, and have really paved the way for also a fantastic future of this topic. By the way, if you are interested in using those telescopes, there are now opportunities to put in observing proposals where you can actually tick off boxes for both the James Webb Space Telescope, the VLT, the ALMA, and the VLA in one go. So if you really want to, if you have an idea and you think, I need more than one telescope in order to reach my science goal, there's now a very nice opportunity where you only need to write one proposal, and then it's being reviewed by the time allocation committees of these different telescopes. And if you're lucky, and especially with Webb, you have to be very lucky these days, then you get your observing time. Okay, So let's dive now into angular resolution, because that is, of course, one of the most important things for a telescope. The higher the angular resolution, the sharper the images, the more you can tell about a particular object. And of course, the angular, and apart, of course, from the collecting area, which provides you with sensitivity. So let's talk about angular resolution and then about interferometry. So yeah, I found this diagram on the internet that I think nicely illustrates the big advantage of spatial resolution. So here's a piece of the sky. Actually, I forgot where it is on the sky, so apologies for that, but I think it's in the Magellanic Clouds, but I'm not sure where you see at roughly the same wavelength what Spitzer saw with the IRAC telescope. And Spitzer was a 90 centimeter mirror, primary mirror. And now with the Webb telescope, with MIRI, the mid-infrared instrument that is sensitive from 5 to 28 microns wavelengths, but also with a filter that is sensitive to roughly the same wavelength range, you can see the enormous improvement in spatial resolution, but also in sensitivity by detecting very faint objects in the background, for instance, but also being sensitive and picking up this very low surface brightness filamentary material, which is in the molecular clouds and which is being excited by the radiation of the stars that are nearby. By the way, you can see here that all these stars look like the things you have in a Christmas tree, but that is because of the funny shape of the primary mirror of the Webb telescope and its secondary mirror. So we'll get to that in a moment. So what happens is, in fact, is that these telescopes can be viewed as a screen, where in principle there's an obstacle. So light is coming in from this direction. We have a distant object, so there is a plane wavefront coming in, and and you can imagine that every wavefront is built up of points that are emitting spherical waves again, and so they can be combined into a new wavefront that is then propagating in this direction until it runs into an obstacle. In this case, the obstacle is, for instance, the telescope mirror, for instance, is this size here. But in principle, what this diagram tells you is how diffraction works. So we see that these wavefronts then start to carry on, and we have a modified background, a wavefront behind this obstacle. And so that is actually the principle of how a telescope works, where you can understand the aperture of a telescope as interacting with the incoming plane wave, and then diffraction happens. And so if you think of a telescope as a circular aperture, the Fraunhofer diffraction can be seen as the intensity as a function of angle is a normalized intensity times the Bessel function, where this parameter x is k times a times sine theta, and it gives you a number of 0 points. That's because of the shape of the Bessel function at these angles, sine theta. So the zeros of this J1 function are at these values of x, are at 3.83, etc., and you can express this then. You can expand this sinus theta, approximate this with this formula here, which is then translating, if you put in the numbers, so 2 and pi of 1.22 times lambda over d, and lambda is the wavelength that which you observe, and d is the diameter of the aperture. And so this is then the area disk of a point spread function of a single aperture telescope. So a telescope which just exists one aperture, a spherical aperture, where you see the central peak, and then the first null here, and then these interference rings due to the diffraction of the incoming wave. And here I have an example of different point spread functions of an instrument on board of the James Webb Space Telescope, which is the NIRCam instrument. And you can see here that these point spread functions are a lot more complicated than just this simple area disk here. And that has to do with the fact that the James Webb Space Telescope mirror consists of a number of segments, and the secondary mirror and the support structure. And they all imprint their signature on the point spread function of the telescope. So that's why a star observed or a point source observed with Webb provides you with an image in the focal plane of the instrument like this. So the angular resolution of the telescope again, you can write down like this. So when can we separate two point sources on the sky from each other? Well, that is, we can just resolve them when the center of the airy disk number 1 coincide with the first minimum of the airy disk number 2, and that translates into this famous formula for the angular resolution in radians, in units of radians here, and the wavelength of the light and the diameter, of course, in the same units. And here's an example of different types of apertures and the different point spread functions, or to say it in other words, images of a point source that these different apertures result in. So here we see the airy pattern of a circular, and then it gets more complicated if you go in this direction, and you end up with the one from the James Webb Space Telescope. A single dish telescope, of course, gives you a very nice angular resolution, but that is not enough to reach, for instance, the inner regions of planet-forming disks. And certainly if you go to longer wavelengths like millimeter or radio frequencies, a single dish telescope doesn't provide the angular resolution to resolve those objects simply because of the fact that the angular resolution is proportional to wavelength. So if you go to longer wavelengths, this angle goes up linearly, and that means that our angular resolution becomes poorer and poorer. And that is why interferometers are so popular. And so here are a few interferometers, and these are the same ones I showed you in my first slide. So let's now look into the principle of interferometry. And of course, what interferometry does is, why do we do interferometry? That's just because in principle, we would like to build a telescope with an aperture which is large enough to angularly resolve the objects that we are interested at the wavelength that we're interested in. But that would, for some scientific cases, mean that we would need to build telescopes of many kilometers in size, and that's of course not practical. And so what people do is then they make interferometers, and that just means that you sample the aperture of a large telescope by many smaller apertures. And that has the advantage that the angular resolution that you can reach is the same as that of the largest separation baselines between two elements in your interferometer. But of course, you can see that there is a lot less collecting area, and therefore your sensitivity to very faint objects is maybe not as high as when you would have to fill this entire large gray aperture and would have the big telescope. And because you sample this aperture, this gray aperture, sparsely, your image quality, of course, can also will be less, and you have to work hard to get back and reconstruct the images that you would have been able to take if you had a full aperture. So we have the sky image, we have the pupil. In this case, the pupil is not a single telescope, but two telescopes. And then at the detector, we let these two pupils interfere, and then you get this interference pattern that we are interested in, and that encodes the spatial information of the object as if it were observed with a telescope with the diameter of the separation of the two pupils. And the basic principle behind interferometry is the van Sittert-Zernike theorem that tells us that the coherence of radiation between 2 points that reach on the sky that reach the telescope or reach the aperture is an integral of the intensity, which is this term here, and then this term is the Fourier transform of that intensity. So the coherence of radiation is actually a Fourier transform of the intensity of your object on the sky, and this is being used in interferometry because we can measure with the interferometer this quantity here, which is the complex visibility of the signal, which contains the amplitude and phase information of the signal. If you do that for many different telescopes, then you can actually reconstruct the image. And often the coordinates that are used are not in the projected baseline lengths, in this case in direction x and y, but they are normalized to the wavelength. And so then we call them U and V. So if you read papers about interferometry, you will see a lot about the UV plane, which is the plane in which in which you can project the different baselines. And if you have many different baselines, of course, your image quality improves. So again, this is what we can measure is the complex visibility of the signal. That is the output of the interferometer, and that has amplitude and phase information. And so here's an example of both amplitude and phase. So here is a point source in infinity, and we have here a screen, which is our interferometer with two apertures. So two telescopes are being combined here. And then we let that signal interfere, and you can see that and then what we get are so-called fringes, in which the signal either interferes fully and we get a strong positive signal, or they completely negatively interfere and then the signal goes to zero. So the amplitude between this peak and this valley here is called the fringe amplitude. And the spacing between them is lambda over b radians. And here you can see how you can get the phase of the visibility, which is the geometry of the source. So for instance, we have 2 point sources here that are observed with the same screen, and you can see here that these wavefronts are slightly tilted with each other, and so that means that the fringe pattern shifts to the left or to the right, and so the phase of the visibility gives you the geometry of the source. So the amplitude gives you the amount of flux that you have between 2 points, two element interferometer in this case, and in this case you get and here you get the phase. So to put that in a different diagram, the visibility amplitude in the UV plane it's either fully constructive, so we have the maximum, or it goes to zero when you are in the destructive minimum, and then it goes, if you go to the next peak, it goes to the maximum again, etc. And the phase, the visibility phase, shifts between 0 and 180 degrees. Okay. You can play a lot of games with these fringe contrasts. So here is another one, just to help you understand the principle. Here you have a fringe of a point source which is monochromatic, with in this case an example at a wavelength of 2 micrometers, and then if you then make that source extended, what you get is that the spatial signal from different parts of your object come in at slightly different phases, and they add up in a certain way. And that what happens is that because of the smearing out of the different phases, your fringe contrast actually goes down. And that means that you actually spatially resolve the object. So from a not spatial resolved object, perfect point source, to an extended source, you can see that the fringe contrast decreases. The same actually happens if you add wavelengths, because the wavelengths fringes also shift with each other slightly, the phases of those fringes, and that means that it also is smearing out, and that has a slightly different effect on the fringe patterns. And then, of course, here in the lower diagram, if you have both spectral smearing and spatial smearing, then the fringe contrast changes in this way. How do you do this in practice? This measurement of these of the fringes. Well, you have in this case, just the simplest case, we have a two-telescope interferometer. And what we need to do is to, in principle, we want to have these two telescopes in the same, act as a single telescope. And that means that we need to compensate for the difference in the path lengths. Because we can't put the telescope here. We would like to put it here, but that's just not possible. So we have it on the ground, and that means that we have to compensate for the path length difference, and that is done in a delay line. And then after the signal has gone through a delay line, so this one has to wait a bit before it can be combined with this one, which is en route a bit longer. And after it passes through this delay line, you have a beam combiner that then creates the interferometric signal, which are the fringes. So the amplitude of the visibilities is measured by varying this path difference between the two telescopes, and then that's the most direct way to measure the amplitude of the visibilities. And the phase measurement, that is really a lot harder because of the fact that both the atmosphere and the telescope add phase shifts to the individual signals of the telescopes, and therefore you cannot just directly measure the phase so easily. The amplitude is also somewhat of a challenge, but it's certainly more easy to measure the amplitude by scanning the fringe contrast. And what people do to still get a phase measurement, and remember the phase tells you about the geometry, which is of course one of the important things to measure, is I first have a few examples of visibility curves, excuse me, of different objects. So here is a visibility curve of uniform stellar disk. So there are two examples here. So this is for a particular telescope setting with a particular distance of the interferometric elements. For assumed size, angular size of a star, so a uniform stellar disk is being assumed here. 3 are milliarc seconds and 1 milliarc second, and so if the object is small in the sky, this is then the visibility for the longer and longer baselines. It goes down because as you go to longer and longer baselines, you spatially resolve the object more and more. So the fraction of the light which is completely coherent goes down and down, and therefore the visibility goes down. And here the object is so large compared to your interferometric baselines that you can actually not only resolve it completely and go out to what we call the first null, but you can also see these other lobes, the first and second lobe, and these contain information about, for instance, if your object would be not uniform, but would have a non-uniform surface. So you can then start to probe things like star spots, if they would be big enough to cover a significant fraction of your stellar disk. You would be able to see them in the shapes of these curves. And here's the visibility of a planet-forming disk as an example from a paper by John Monnier, where you see that the visibility is very high for small baselines. So here's the baseline in meters. And then if you increase the baseline length, the visibility goes down because we zoom in and less of the flux is correlated. And then this particular shape here is completely governed by, this plateau here that we reach here is completely governed by the amount of flux of the central star, because if you go to longer baselines, you begin to resolve out the spatial emissions from the disk itself, and you're only left with the visibility signal of the unresolved central star. That's also depicted here in this diagram, where in this case it's not visibility but visibility squared, where as a function of baseline, again for a planet-forming disk, visibility goes here from very high values, so you hardly resolve the disk, and then the visibility goes down to an asymptotic value, and this is set by the contribution from the star. So by measuring, for instance, where this settles, you can actually tell what fraction of the total flux you measure from the star and disk at a particular wavelength comes from the disk, and what fraction comes from the star. So I mentioned earlier that measuring the phase is very difficult, but there's a trick to this, and that is by using not 2 telescopes, but 3 telescopes, and measuring the so-called closure phase. Because if you have a telescope, if you have a setup like this with 3 telescopes, and you have an object, a source on the sky here, and with 3 different telescopes with their own local induced phase shifts, and those phase shifts can be due to the atmosphere itself, but also due to the instruments and the things that happen to the signal once it's in the telescope receivers. And so you can write the total phase between 2 telescopes, in this case 1, 2, 2, 3, and 3, 1, as the interferometric phase of the real signal that you're interested in, plus the phase difference that is added between telescopes 1 and 2 due to everything you don't want to know, and that disturbs the phase. So phi 1 minus phi 2. And you can do that also for telescopes 2 and 3 and 3 and 1. And then you can see that if you add all of these up, then the disturbing effects from the atmosphere and telescope are cancelled out precisely, and then you're left with the sum of these 3 phases, which is called the closure phase. And for a spherical object, those closure phases will be 0, but for non-spherical objects, they will have a certain value, and that is then, of course, the information you can use to reconstruct your image with different techniques. And so if you have more than 3 telescopes, and this is the one, an example with just 1 added, we have not 3 but 4 telescopes, you can actually measure a number of closure phases. In this case, there are 3 independent closure phases you can measure. And that means that that helps you enormously in gaining enough information about how these different phases, the values of these different phases as a function of the orientation of your baselines on the sky, that you can then start to reconstruct your image with the reconstruction algorithms. Then another very important and very clever trick that people use to increase the UV coverage, so the sampling of your point spread function of your interferometer, is by using the Earth rotation. And then you get these types of diagrams where you have here the UV plane again, in this case measured in meters. And every dot is an interferometric pair that tells you where it is in terms of distance, but also where it is in terms of angle. And then you can imagine that all these different green points are due to the rotation of the Earth. And so this really is physically only a single telescope baseline, interferometric baseline, but then the Earth rotation makes the projected baseline on the sky different in terms of angle, and therefore you can use the Earth rotation in order to improve your UV coverage. Okay, so much for angular resolution and interferometry. Then I thought it was maybe good to dive into two telescopes that are very important for astrochemistry. One is the James Webb Space Telescope, and the other is ALMA. So let's now first discuss the James Webb Space Telescope. Yeah, so first this one, and then the ALMA telescope. And here you see a nice image of the telescope with its primary mirror, secondary mirror, its sun shields, its housekeeping equipment down here, and the instruments that are behind the primary mirror. So this is the instrument module here, the ISIM. So this is a fact sheet. So the diameter of the primary mirror is 6.5 meters. So that gives you a clear aperture, not obscured by the secondary mirror or the support structures, of 25 square meters. So that's quite challenging. It's a beryllium coated mirror that only weighs 700 kilos. So it's really very lightweight because of the beryllium. Well, a few other numbers, you can read them maybe later on when I put the slides online for you. An important thing is the wavelength coverage here, and of course the angular resolution, 0.1 arc seconds at the optical. Of course, goes down with wavelengths to typically 0.2 or 0.3 arc seconds at the longest wavelengths. The wavelength coverage is all the way into the optical until the mid-infrared, 28 microns. It has a very large sun shield of 21 by 14 meters, which consists of 5 different layers, and that take care of the cooling of the telescope simply by passive cooling. There is a cryostat for there are coolers for one instrument, MIRI, but there's no cryostat or no helium that's being consumed to cool it. So it's all passive cooling and mechanical cooling. The orbit is 1.5 million kilometers from the Earth, so it's orbiting the L2 point. And the telescope is cold, of course, because we want to observe cold things in space. Therefore, you want to avoid that the telescope itself radiates, and that is why it has these enormous sun shields, and so the temperature is now under 50 Kelvin. And the gold coating on top of the mirror is really a very tiny. So it actually has a very low mass of gold, but of course very crucial to have the reflectivity of the telescope mirrors. Yeah, so this is a more detailed description of the different elements of the telescope. Of course, the very important part is the ISIM, is the science instrument module, which is behind the primary mirror, and of course is completely in the cold, in the shadow, in order to keep the instruments as cold as possible, because otherwise the detectors would not work. And here's an older picture of the ISIM, where you can see where the different instruments are being located: NIRSPEC, NIRCam, MIRI, and the fine guidance sensor, with IRDIS also included. Sorry, with NIRIS included. And here you have an overview of the different capabilities of Webb. And I mean, if you go to the website of Webb, and click on the different instruments and their capabilities, there's an enormous choice and richness in different observing modes with different combinations of filters and spectrographic elements and selecting different wavelength ranges. So that would be just impossible to go through during this lecture, but I thought this might still help you to get a sort of first level overview of the different imaging and spectroscopic capabilities of the telescope with the different instruments. And so if you're interested, I suggest you go to the website and look at your favorite instrument and see what kind of modes you would like to use for your observations. One very nice thing about several of the instruments on board of Webb is they have an integral field unit. And what does an integral field unit? It just slices up the images into indeed spatial slices, and per slice puts it through a spectrograph. So it makes a spectral dispersion of the sliced image, and then puts it on the CCD or on the detector array, a two-dimensional array, and then with data reduction techniques, you can then reconstruct what the image must have looked like as a function of wavelength. And so you then get a three-dimensional data cube where two of the dimensions are just the sky coordinates, right ascension and declination, and the third coordinate is the wavelength. And so you can then, if you have a data cube like that, you can just click on a pixel, and then what pops up is the full spectrum that was observed with the instrument on that pixel. And that, of course, is an extremely powerful way to get information about what's going on, because it combines actually information from spatial information and spectral information. So that is being used a lot now also in James Webb, but there are many other instruments that use integral field units, so it's certainly not unique to Webb, but it's actually a very powerful way to get these data sets. And here for MIRI, which is one of my favorite instruments on board of Webb, and then in particular for planet-forming disks, because that's also a favorite object of mine, so please apologize for this strong bias. So the spectroscopic capabilities are in this range. We have a spectral resolution between 1300 and 3700. So to give you an idea that spectrum resolves gas, which is typically a few tens or 50-ish kilometers per second. So we cannot resolve things that are spectroscopically resolved, things that are in the outer disk that are cold, that are typically at 1 kilometer per second, but we can certainly begin to spectrally resolve lines in the inner disk where they are typically 50 or so kilometers per second. This is a field of view. It's only a very tiny field of view. Of course, you pay a penalty for these integral field units, and you fill the detector array, which has 1 million pixels, very quickly. So you can only get to a limited field of view, but of course the great gain is that you then get a spectrum per pixel. Like MIRI, also the other instruments have the capability for integral field units. And then for the imaging, MIRI has several filters. The IFU, the IFU has this field of view. I don't see the spatial information on this slide for the imager. So that's something I'm missing here. Anyhow, so, and then of course there's also a coronagraph. There are several coronagraphs on board of Webb. So if you want to observe faint things around bright objects, like we've seen in the example of the orbiting planets, you can also do that with Webb. Okay, the second telescope which is important for astrochemistry is ALMA, and so let's dive into ALMA for a few slides. So this is the ALMA site in the north of Chile, in the Chilean desert, the Atacama Desert, at 5,000 meters altitude. And the reason why ALMA is built in such a high place, even higher than the VLT or even higher than the top of Mauna Kea, is because you want to have as little atmosphere, Earth atmosphere above your telescope, because the atmosphere is still a nasty thing at these at the wavelengths at which ALMA is operating. So this is the this is the consortium. This is the international collaboration that runs the ALMA telescope at NRAO in the US, the European Space Agency, and NIOJ in Japan are the main groups that have formed and built ALMA. Here are a few facts. So there is a large array and a compact array. The large array is 12-meter antennas. So the diameter of the individual antennas is 12 meters with baselines up to 16 kilometers. That has the highest angular resolution. Of course, the largest baselines are 16 kilometers apart. And a compact array has 12 antennas of 7 meters and 4 antennas of 12 meters. And that gives the largest spatial scales. Sorry for the typo here. And that gives you an enormous range in spatial resolution from half nanosecond for the smallest separations to 20 milliarc seconds. So that really gets you to the inner regions of planet-forming disks, as an example, again, at distances of 100 to 200 parsecs. Observing frequencies are also a very wide spectral range, cut up in different bands 1 to 10, and these have to do with the atmospheres of the transmission of the Earth's atmosphere, and this spreads between 35 and 950 gigahertz. And because of the fact that ALMA uses heterodyne detection of the signal spectroscopically, the spectral resolution can be very large, up to less than a kilometers per second, even much less than a kilometer per second. But that can be set in the different settings of the different receivers. Yeah, here you see the different spectral bands of ALMA, and so this is a plot again of in this case of frequency here on the horizontal axis and the transmission on the vertical axis, and unfortunately, there's still a lot of interference of the Earth's atmosphere, so that's why ALMA has been designed to detect, obviously, in spectral bands where the atmosphere is transparent, and you can see here the band numbers going up with increasing frequency or going down with lower lower wavelength. And the three different curves here give the different water content in the atmosphere: 0.5 meter, 1.5 or 2.5 millimeter. So that gives you you can see how strongly the atmospheric transmission can still vary, especially for the higher frequency bands. So the higher the frequency, the more difficult it is to observe with ALMA. But it of course has the great advantage that for higher frequencies, the angular resolution goes up dramatically, linearly with wavelengths, so that makes for much sharper images. And this is just an example of the UV coverage. The one I showed you earlier was for a VLT interferometer, and this is now what you can get for ALMA. So you can see here that there's an enormous dense UV coverage, and then you can reconstruct really extremely sharp images where you can see a lot of detail in the spatial distribution of the intensity of the object. Okay, sorry. Yes, so far for everything I wanted to tell you about telescopes. Now I think we can switch gears a bit. So maybe we can take a minute just to let things sink in, and then go on with the second part of my lecture, where I thought it was nice to talk a bit about one of my favorite topics, which is solids in space, and give you a bit of a flavor for how we think that the solids in space evolve from where they are formed until when they are incorporated into planetary systems. So let's maybe, because of the time, I think maybe just dive into it straight away. Okay, so why should we care about solids in space? Well, there are a number of very important reasons. First of all, they are a source of opacity. Solids, when they are in interstellar clouds or in circumstellar environments, they absorb radiation, they re-radiate energy because of the fact that they are heated up. And so they are important for the thermal balance of interstellar of the interstellar matter of molecular clouds, but also of planet-forming disks. They provide the surface. As Ted Bergen has been showing in his lecture, molecules, like the most important molecule H2, it can only be formed on the surfaces of dust particles. So they're a very important site for increasing molecular complexity by just having these atoms accrete on the surfaces of those grains and meet other atoms to form molecules. And an example, for instance, the molecular formation of H2 in interstellar clouds. And then, last but not least, we know that the rocky planets and the cores of, very likely also the cores of gas giant planets are made from solid material that enters planet-forming disks. So a lot of reasons to look at solids in space. How much of the material actually, if you take a typical molecular cloud or an interstellar cloud, how much of the solid, how much of the atoms is in dust? Well, that's only 1%. So although it's mass-wise not a very important thing in terms of its impact on what happens on the processes in interstellar space, it is a very important component. If you ask what is interstellar dust and circumstellar dust made of, if you focus on interstellar dust, there are actually two dominant species. One is oxygen-rich, built up from an oxygen SaO4 tetraeder. That's the main building block. And then we have carbon-rich dust, which can be have different structures. You can think about amorphous carbon, but also graphitic material, and then all kinds of other very small carbon-rich molecules like polycyclic aromatic hydrocarbons. We think that the main sources of dust those are evolved stars, asymptotic giant branch stars that have a slow wind. We'll get to those, or red supergiants or Wolf-Rayet stars, but also supernovae and novae add to this. If you add up all the dust production sites that we know of in our galaxy, and then you calculate how fast dust gets destroyed in the ISM because of shocks by supernovae and other energetic processes, then you get into a dust budget problem, because there's not enough dust produced by those stars to account for the amount of dust we actually observe in the ISM. So that means that there must be a site of dust formation in the ISM, and that's very likely where the densities are high and molecules and atoms can stick to pre-existing dust particles, and those are molecular clouds. So although it's not really fully understood how that works, this is the general idea. That molecular clouds are important also for dust production. So if we zoom into central stars, if we zoom into HEB stars, asymptotic giant branch stars, as dust formation sites, you can think of those stars as very extended, very cool objects that are pulsating, and through their pulsations they eject matter into interstellar space through a very slow, dense wind. And because of the densities and temperatures in the outer regions of those envelopes of these evolved red giant stars, atoms and molecules can actually go from the gas phase into the solid phase. And then what happens is they are receiving radiation from the central star. They experience radiation pressure, and they are pushed out. They drag along the gas, and this is the reason why these stars have stellar winds. And so dust is actually very important for driving red giant winds. Depending on the flavor of the red giant star, you can either have red giant stars that have more oxygen than carbon, or more carbon than oxygen. You either form molecules and solids that are oxygen-based or carbon-based. And here I have an example of actually a pre-solar grain that was found in a meteorite, and so this grain entered the solar system and survived the formation of the solar system, and it is made of graphite, which is the main part of this grain. But you can see that there is a core of titanium carbide in here. And then if you think about where material can condense in chemical equilibrium, this is from Lodders and Fakeley here. You see the pressure on the horizontal axis, 10 to the minus 4 to 10 to the minus 8. So we go down in pressure here, and we have the temperatures here, and every line here, and this is for a carbon of an oxygen ratio of the gas mixture of 1.1. All these lines depict where at that particular temperature and pressure, a particular material goes from the gas phase to the solid phase. And so, this apparently in this diagram, under these conditions, graphite and titanium carbide require temperatures of the order of a bit more than 1500 Kelvin, and pressures of the order of 10 to minus 8 or 10 to minus 7 or so bar in order to condense. So this gives you actually from a pre-solar grain, which is older than the solar system. I always find that fascinating to think about. A direct picture of how dust condensation in these evolved stellar winds actually proceeds. As I said, there are two main sources of stardust. One are these red giants, and here you see a picture of, in fact, a planetary nebula, which is the end phase of the evolution of a red giant star. You can see all this debris has been ejected over hundreds and thousands of years, because this is a very large scale of this image here. In fact, a very famous planetary nebula called the Cat's Eye Nebula. And here you see the Gas A supernova remnant, which is the other type of stardust that is very likely important, and that is produced during supernova explosions. Also from pre-solar grains, we know that supernovae produce dust that is then found in these meteorites, although at very, very tiny abundances. What we still don't know is the relative contribution of these evolved stars and massive stars to dust production. And so that is a topic of ongoing investigation, in fact, also with ALMA and with the James Webb Space Telescope. In an older review, Xander Thielens once came up with this rough division of the different sources of dust to the interstellar medium, where supernovae are significant, 30% or so part of the total dust contribution. As I said, this really is still not completely sure. However, there was a recent observation of a distant galaxy in which people have been able to observe carbon-rich dust at a very high redshift. And these galaxies are so young that it's very unlikely that red giants have been around long enough to start producing a lot of dust. And so the dust you see in these very early galaxies must have been due to massive stars that evolve much quicker and then can also produce dust in the supernova explosions. So I think this observation tells us that certainly in the early universe, when at very high redshift, simply because of the lifetime of HEB stars being too long, the dust production at those epochs must have been dominated by supernovae. So that tells us that supernovae are an important source of dust, at least in parts of the history of dust production in the universe. If you want to understand dust, it's maybe good to go a bit into details about how dust particles interact with electromagnetic radiation. So I prepared a number of slides that discuss scattering, absorption, and emission of dust particles. And yeah, so the basic principle is like this. It's not more complicated than this. We have an incoming ray of radiation. We have a small dust particle, which is of a funny shape, which complicates matters actually a lot. And it can do two things. It can scatter light, so that means that the photon is redirected, so it doesn't change in energy, but it is just redirected out of our beam to into another direction. And what it can also do is it can actually absorb photons by and then that energy is added to the thermal bath of the particle, and that gives it the temperature, and therefore it radiates at some equilibrium temperature, and that is always in the infrared. And so that means that thermal emission is emitted by these dust particles. And here you see a very nice picture of the Horsehead Nebula that I always like to show, because it illustrates both the absorption. You can see here this dark shape, which is basically everything that is in this bright nebula, which is behind this molecular cloud structure, is being absorbed. And you can see here in this lower part, this lower corner of this picture, a star which is emitting a lot of photons, and there's a cloud in the line of sight of, or maybe even close to that star, that is scattering photons. So we see here the effect of dust scattering. So both absorption and dust scattering in a single picture. Here's another example of a planet-forming disk. Again, apologies for my bias towards these objects. Here you have an image taken with two different telescopes of the same object. So it's really amazing to have these two different images of the same object with such a different geometry. And the secret behind this is that in this planet-forming disk, which is very, very nearby object, TW Hydra, we see here in the near-infrared the light of the star that's being scattered off the disk surface towards the observer. So the photons are being emitted by this central object, which is not seen here because it's obscured by a coronagraph. And then the stellar photons are scattered towards the observer, and that's why we see all these bright rings. And of course, there are also regions apparently where there are less scatterers, so that's why we see a dark ring here. And these particles are sitting at the surface of a disk because they have to be in direct view of the starlight. And then here with ALMA, you have a similar picture of the same disk, but that looks completely different. And here we look at a very different phenomenon, namely the thermal emission of cold dust grains. They are big, they are pebbles, grown to millimeter sized, and they are in the disk midplane because of their settling to the disk midplane, and they are cold, and they can be observed with ALMA. And here also you see these rings of material. Apparently there's a lot of structure in this disk, and that is very likely due to the ongoing planet formation. So examples of scattering and thermal emission of dust particles. Yeah, what we do then, just to set the scene, is we have a cloud of dust and gas, of course, because remember, the main part of interstellar clouds are H2 gas, and dust is only 1%. So we have an object here that is obscured by a dust cloud, and we observe this with our telescope. And then you can write a very simple radiative transfer equation. It's the simplest possible radiative transfer equation. The intensity we observe at the telescope is the intensity of the object, diminished by the optical depth of the dust cloud. And then the cloud itself can also add radiation, and that's described in this term, where we assume that the source function for the dust particles that is radiating is the Planck function in this case. So we just assume here, for simplicity, that they are radiating like black bodies. And then with this term, 1 minus e to minus tau nu. With the variable, so optical depth is the number density of particles times the length of the line of sight through your cloud times the opacity, kappa nu. And then you can rewrite this also by combining the number density and the length, because often you don't know either one, but you do know the product of the two, which is a column density in parts per particles per cubic per square centimeter. So then we go to this very simple radiative transfer equation. So where we have the diminishing of the intensity is proportional to the intensity times the number density of dust particles times the length times the extinction cross section, which has two components, absorption and scattering. And then it's trivial integration. You can get to this equation here, where you see that the intensity you observe is I naught times e to the power minus tau. So this is where this exponent comes from. And where you can write the optical depth like this is the number density of dust particles. So it's the column density of dust particles times the extinction cross section. And then it's convenient to introduce extinction cross sections in terms of these Q factors, where Q extinction is the sum of Q absorption and Q scattering, and that is just the extinction cross-section divided by the geometric cross-section of your particle, pi a squared, where a is the radius of your dust particle. And then the extinction coefficients Q depend on a parameter which is introduced here, the parameter called x, which is 2 pi a over lambda. And these extinction efficiencies depend on this value x, but they also depend on the composition of the particles, namely the complex refractive index of the grain material, and they also depend on the shape of the particle, whether it's a sphere or an ellipsoid or an irregular part. And the complex refractive index is written like this. It's m. The symbol uses m. It's wavelength dependent, and it has a real and an imaginary part. The real part is n, and the imaginary part is k. And n and k are called the optical constants, and they depend on the different materials. So these are really the material properties. That's something to remember. So x is 2 pi a over lambda. If x is much smaller than 1, then we're in the Rayleigh regime, which means that the particle is much smaller than the wavelength, and so we have what people call Rayleigh scattering. For x is about 1, so if the dust particle is roughly of the size of the wavelength you're observing it, then there are no simple solutions. You just have to do the math. And for x much larger than 1, you have the geometric optics regime. So going back to this complex refractive index, maybe you can get a bit of feeling for what these different terms mean physically. Well, the real part actually describes the scattering, and the imaginary part describes the absorption. And the way to visualize this with a bit of math is if you consider a wave traveling through a medium with a complex refractive index m lambda, then you can write the wave propagation like this in vacuum. But then if you go into the medium, so into the dust particle with this complex refractive m, you can show that then the amplitude of the wave and the time variation of the wave as it propagates changes into this term here, into this equation here, where you have added, where there's an extra term here, the exponent, this exponential term is introduced here. And, oops, sorry, where am I? Excuse me. And so the second part here, really you can see this e to the power minus kx. So if you go into the dust particle deeper and deeper, your amplitude of your electromagnetic wave goes down. So you absorb radiation. And that energy is then dumped into the vibrational modes and the vibrations of the lattice. And then, for instance, for isolators, you can imagine that the field cannot easily penetrate. So that means that k is roughly 0. So you really have only the real part of the refractive index. And then you can write that m is n. And that is often can be approximated by this formula here, based on material properties of isolators. Me theory is then developed in order to describe the interaction of electromagnetic radiation with a spherical dust particle. And that's really a boundary value problem. What the theory does is it just demands that the electromagnetic field is continuous across the boundary of the particle. And me theory, it's a fairly if you look into it, you can develop mathematically into a series expansion in the size parameter x is 2 pi a over lambda, and then if you look only at the terms that are relevant in the series expansion for small values of x, then you get to these expressions for q ups and q scattering, how they depend on epsilon, and how these epsilons depend on the complex refractive index is given here, where epsilon is the dielectric constant. But to make life easy, there's a simple recipe to remember that the q ups is typically 1 for lambdas, for wavelengths that are small compared to the size of the particle, and they go as 2 pi a over lambda for wavelengths much larger or larger than 2 pi a over lambda, and for scattering again goes to 1 for lambda is smaller than 2 pi over lambda, and it goes to 2 pi a to the 4, so it goes as a to the 4, but lambda to the power minus 4 for a large wavelength compared to the wavelength is larger than the size of the particle. And so you can see here the Rayleigh scattering lambda to the power minus 4 popping up. Yeah, then you can plot Q as a function of x for, in this case, a particle which has this refractive index, so it only has a real part, no imaginary part. So Q extinction is Q scattering. That's why you see only one curve, and you get this wiggly interferometric pattern, which is really the interference of the incoming wave, the transmitted wave, and the emitted wave of the dust particle. That gives you an interference pattern that looks like this as a function of x. And in the end, this value of x actually reaches an asymptotic value of about 2. And here's another example where there is actually a small imaginary part of the complex refractive index. And where you can see here that actually the salt curve is the total extinction, so Q scattering plus Q absorption, and for small x, so for when the particle is small compared to the wavelength, then the scattering becomes unimportant because that goes as wavelength to the power minus 4, and only the absorption dominates. So that's why the total curve here and the dashed curve come together. So in this regime, you are dominated by absorption at small values of x. The absorption cross sections, as I said, also depend on wavelengths. And so here's an example of a mixture of both carbon and silica dust, taken from a paper by Michiel Min, where you see as a function of wavelengths the absorption cross section, the absorption kappa. So this is no longer Q, but now we are back to kappa in centimeters squared per gram. And the reason why I show this diagram is to imprint on you that there are also in solids, you can actually see the resonance of stretching of molecular stretches in the solid. In this case, we have SiO stretch and bending resonances, and at those wavelengths or at those frequencies, the opacity of the dust particles go up, of course, because in that resonance, the cross-section, the probability of absorbing a photon or emitting a photon actually increases. And you see the peaks of these two clearly imprinted on the wavelength dependence of the opacities here. So this is a way also to then, of course, if you know from laboratory measurements what these curves look like, you can then compare them to observations and then infer what kind of materials you have in interstellar space. We can also measure dust masses. So assuming, for instance, the dust is cold, so we have the Rayleigh-Jeans tail of a black body, we assume that the dust is optically thin, and we can also assume that the dust grains themselves are optically thin. Then you can actually measure the dust mass, but of course you still need to have a value for the optical for the opacity of your dust grains, and that depends very much on where you are, or in other words, what is the mixture of the dust that you're observing? Is it icy or is it without ice? That, for instance, makes a lot of difference. So knowing this kappa nu is one of the tricky things in measuring dust masses anywhere, whether it's a supernova explosion with dust or whether it is a circumstellar a disk. So let's now talk about, so that was a bit about the basics of scattering and absorption of dust particles and opacities. Now let's dive into ices and refractory dust. And so taking it from the molecular clouds, here you see a spectrum of a background object which is in front of a cold molecular cloud in which you have a lot of ices. And so this is actually still a pre-James Webb spectrum, but I think it shows the point. You see a very deep absorption because of molecular species that are in the ices that are in this cold molecular cloud and that are absorbing radiation from the background object. And by looking at the wavelengths and the shapes of these absorption bands, you can derive a lot of information about what kind of ices there are, like water or methane or carbon monoxide or carbon dioxide. Also about the silicates, so the refractory materials here. You can see there there's the 9 micron absorption, 10 micron absorption from the SIO stretch. And by analyzing these spectra, you then learn a lot about how these ices can evolve by observing them along different sidelines and in different places.
Rens, 15 minutes.
Thank you. I think I'm getting close to the last part of the slides. So thank you very much for the reminder. Molecular ices are being formed in these clouds because of the low temperatures and the fact that there are dust particles that are pre-existing. They can act as surfaces. We've seen that, and atoms can accrete onto surfaces of those grains and therefore form molecules. They can then stay on the grain or be ejected again depending on the binding energy. And so you can form actually very complex molecules in these ices, also complex organic molecules that are then later on released to the gas phase again once this particle heats up in the neighborhood of a young star. And here's an example of what people think would be the formation route of water on the surface of such a dust grain, where you start, for instance, with atomic oxygen together with OH to go to H2O, but you can also have more complicated routes that go through molecular oxygen that is then hydrogenated and in the end also produces water. So different routes in these ices to form water ice, which is the most abundant ice we find in cold interstellar clouds. Other important ices are carbon monoxide ice, CO2 ice, methanol ice, and methane ice. And again, just to remind you, why we see these ices, why we see these absorption bands, these are the vibrational resonances of the binding blocks, building blocks of those ices. So either depending on what kind of ices you have, a CO stretch, or a water or hydrogen bending mode at the various frequencies that these that you can find that these resonances are founded. And obviously, these molecules don't show any rotation anymore because they are in the lattice. So you only see the collapsed rho vibrational bands as a broad absorption band in these spectra. So that's the difference between the gas phase and solid absorption. We'll see an example in a moment. Yeah, and so here again, same example of a strongly absorbed background object, a massive YSO in this case, that has a lot of molecular cloud ices in front of it, with the different ices depicted in this diagram. And here's a diagram where you see how the different ice abundance increases with increasing optical depth of the cloud. So as you go deeper and deeper into the cloud, or as the radiation is more and more shielded, the radiation from outside, from the UV radiation from the stars, more and more molecules can start to form, and you start forming water first, and then CO and CO2 ice, and then methanol ice a bit later. Then if you heat up these ices, the molecules can go into the gas phase again. And this is an old diagram from Emilio van Dishoek that I really like to show, because it so nicely shows that if you go from a cold region to a hot region, ices evaporate. And for instance, you first have a very cold source up here with a lot of CO2 and CO ice, but then you see the ice evaporate first, the CO ice, and you see the rho vibrational gas phase lines appear, but the CO2 ice still stays in the solid phase, because the sublimation temperature for CO is lower than from CO2 ice. And so if you heat up the source even more, then you basically have lost all your CO ice, and there still is some CO2 ice left. And so this can be used also as a probe for, to what extent is the sightline being heated up, and are you going back into the gas phase? And then we go into the planet-forming disks. You've seen a lot of examples there. Yeah, I'm going to skip this diagram in view of time. But in principle, if you think about where the different elements end up, either they end up in rock-forming elements in rocky planets, or cores of gas giant planets, and a lot of these elements condense at high temperatures. So these are what we call refractory elements that form the cores of rocky planets. And then there are volatile elements that actually are mainly staying in the gas phase, although there are some that are doing both. And so they are really the main building blocks of, let's say, the atmospheres of gas giant planets after the cores of those, the rocky cores of those planets are formed. And there are some chemical elements that are sort of in between. They have an intermediate condensation temperature. So their behavior is less obvious. You can look at the different types of silicates in those disks as well. For instance, here's a spectrum of an amorphous silicate, where we have a lattice structure which is chaotic. And if you order that lattice structure, you suddenly see a completely different infrared spectrum, and that has to do with the different resonances in the lattice that are done becoming more, they split up because of the ordering of the lattice. So you see different groups of molecules resonate and produce peaks in the infrared spectrum. And to go from amorphous to crystalline silicates, the only thing you need to do is just heat them up, because you just add enough energy for the amorphous and chaotic lattice to become ordered. That happens typically at temperatures above 800 Kelvin. And then once the lattice is crystalline, it usually stays crystalline, even if it cools down again, because it's energetically more favorable. So by looking at the lattice structure of, for instance, silicates, you can trace the thermal history of those dust particles. And surprisingly enough, if you look at a comet in the solar system, like the comet Hale-Bopp here in this picture, or in a planet-forming disk, you see actually a lot of cold crystals, and especially a comet is very cold. So it's formed far out in the solar nebula, so it should not have had these crystals. And that's the signature of the solid material in disks that have seen in high temperature, but that end up in very icy objects like comets. And so there is this interesting picture where you have a planet-forming disk with a star here, and very close to the star, the temperatures and pressures are high enough that you could actually have solids in chemical equilibrium in the inner disk. But in the outer disk, we think that you're really dominated by ices that are, and silicate cores that enter from the molecular cloud and flow into the disk and then are mixed in with the material from this inner disk, which has been forming under chemical and has been processed under chemical equilibrium. And so one of the big questions is how primitive actually the solids are in a planet-forming disk. So it's very likely, based on the evidence from spectroscopy of comets and disks, that the solid reservoirs in disks is very strongly mixed, and that mix is somehow due to gas phase condensation in chemical equilibrium and interstellar icy solids that are coming in from the outer disk. And there is some evidence that refractory solids in planet-forming disks and therefore also in a protosolar nebula might have been formed in the planet-forming disk itself. So the entire memory of what the solids would have looked like, the refractory solids, would have been lost in the protosolar nebula. And then, of course, one of the big questions is what happened to the ices? Are they indigenous? That is, are ices also formed in planet-forming disks, or are the ices inherited from the molecular cloud and that feeds the disk? And so these are things that is sort of at the edge of what we are now thinking about, and current research is focusing on these types of questions. Okay, that was a lot in almost 2 hours. I'm running out of steam. I'm sure you also get tired. So with this, I would like to thank everybody for paying attention and being present at this lecture. And I hope, that you have enjoyed it. I certainly enjoyed it. And so if there are questions, I will try to answer them. Thank you very much.
Thank you, Rens, for this very interesting lecture. So students are encouraged to ask questions now in chat. So we have already some which were asked during the lecture. So I will start with the first question here. The elements of the interferometry telescopes looks as if they are distributed randomly on the ground. Is that right? And if yes, why?
Well, that's actually a very crucial thing. So no, they are not random. They are placed in such a way, and actually they can also be moved, like the ALMA telescopes can be moved. And the trick is to do this in such a way that you sample the UV plane in the most efficient way in order to reach the spatial resolution you need, but also to make sure that the point spread function that the telescope then in the end has, once you have combined all the different interferometric pairs, that you get a PSF, a point spread function of that interferometric telescope that is as good as you can get it with the amount of telescopes that you have available. So there's a lot of thought has gone into placing telescopes and designing the arrays in such a way that you actually sample the right parts of UV plane. And it also depends a lot on the science case. For instance, ALMA has a compact array that samples short baselines. So if you are mostly interested in getting, for instance, a very accurate flux of an object, or the object is rather large, so you don't need a very high angular resolution, then you would rather use the compact array. And if you want to get the highest angular resolution, then you need the full array at the largest baselines. But those configurations are not always offered. And so ALMA operates in different settings, and depending on what kind of configuration of baselines is available, you have to submit a proposal that is following whatever the configuration of a certain semester, of a certain year. So this is, so it's a good question. And there's a lot of thought that goes into these baseline configurations.
Okay, thank you. So the next question. At the beginning, you discussed some CO observations through vibrational lines. The line intensity are shown versus a velocity in kilometer per second. I was wondering, what is the physical meaning of this velocity? I would like, okay, then here ask also another question. Probably you first answer the first one. Okay.
Yeah, sorry that I didn't explain that correctly. So thank you very much for the question. So the velocity is the Keplerian velocity. And so what we use is the Doppler formula, which tells you the relationship between the frequency or the wavelength at which an atom of a molecule emits and the velocity at which that atom of molecule is with respect to the observer. It's basically the same, so it's the familiar Doppler effect. And so gas which is moving away from you is redshifted with respect to the rest wavelength of that transition, and gas which is moving towards you is blue shifted. And if you have an object like a rotating disk, that means that part of the disk, the gas in that disk, will be rotating away from you, and part of that gas is rotating and coming towards you. And that gives you a very characteristic shape of the emission lines that come from such a disk. So those are the two peaks, the two horns that were there. So that is the background of that velocity. It's Doppler shift.
Okay, thank you. So the next question, what is the criteria to define whether a media is optically thin or optically thick?
Yes. Well, optical depths are, sort of, that's a bit of also a very good question, because when you first start to become familiar with radiative transfer, optical depth is really the most one of the fundamental concepts. And in principle, the optical depth tells you if you have a medium which consists of, it could be gas, could be dust, and that medium has a certain density of particles or a certain column density of particles. It tells you basically what is the probability that a photon that is emitted from behind that cloud is absorbed in that cloud. And so optical depth is one. For instance, if you take, let me give an example. If you look at the sun, and you wonder where do the photons come from that I get in my telescope from the sun? They come from the photosphere of the sun, and the probability that a photon actually reaches you, if you have a photon that is deep in the sun, that probability is zero, because there are many different that photon can be absorbed and scattered many times before it reaches the atmosphere of the sun. But at some point, there will be a probability of the probability that a photon will actually reach you will become higher and higher. And typically, we see photons of optical depth 1. Because those are the ones that have a reasonable probability of being produced and then can still escape before being reabsorbed again. So optical depth, so mathematically it's the product of absorption cross-section times the number of particles.
Okay, thank you. So the next question. Are crystalline silicates energetically favored? What mechanism create amorphous silicates to begin with, and why?
Yes, so You can think of this as a freeze out of different reactions that result in the formation of a solid. And if you start out with having a surface and molecules like silicon oxide molecules that are in the gas phase reach the surface of a particle, they can stick, they can collide and stick. But if they do that at a temperature which is what we refer to as below the glass temperature, then the kinetics of that process is such that the molecules that arrive do not have enough energy to reorder into a regular lattice structure. And so when they collide, they just stick in the order that they do. And so if you then grow a particle under those conditions, you would form an amorphous lattice structure. So only if you are above the glass temperature, there is enough vibrational energy in the lattice that you can actually overcome an energy barrier and order the atoms and the molecules in a regular lattice.
Okay, thank you. So the next question, if gravitational waves could be some signature of planetary activity?
Oh, that's a question. Thank you for that question. Now I'm getting out of my comfort zone because I don't know a lot about gravitational waves. Yeah, I'm not sure I completely understand the question of how it relates to planets or planet formation.
If gravitational waves could be some signature of planetary activity, yeah, maybe planet formation, that's what meant. Maybe, yeah, we can get some more explanation in the chat.
I would so my intuitively I would think that gravitational waves, yeah, they are of course a measure of variations in space-time because of moving particles in each other's gravitational field. And those are very, very tiny effects. And so they would not have any effect on what we're talking about here. For instance, the formation of stars or planets. So I think those are unrelated topics.
Okay. Thank you. Yeah, I also have one question from me, because you spoke a lot about interferometry, but in space, is interferometry approach used? For example, why James Webb's telescope is only a single dish telescope? Why you don't send two James Webb telescope in space and to get a much nicer resolution, spatial resolution?
Yeah, well, that of course that is a great idea. Thank you for proposing that. The challenge is that it's very expensive, and so people have thought about interferometers in space. For instance, Darwin was a concept that was around for a while, and now there's a new idea which is basically the same idea, but then in a new concept called life. And the idea is indeed that you then have a few smaller telescopes, not as large as Webb, in space that are infrared telescopes, and they combine light. And you can then, move these telescopes around in the UV plane with respect to each other, or and then combine the light. Practically speaking, the Webb telescope was very expensive. Took 30 years to develop. So I think it will be very unlikely that we will get very soon that type of interferometer in space. It's just technically and economically a very challenging project. But smaller telescopes as an interferometer in space are certainly feasible. And in fact, there is already long baseline space VLBI So where you combine radio telescopes on the ground with one radio telescope in space. I didn't mention that, but that's, of course, then you suddenly have a baseline of millions of kilometers. And that allows you to spatially resolve extremely tiny details of well, non-thermal radio sources, because you need a lot of flux in order to do this.
Yeah, thank you. Because yeah, for me, it's space. It's exactly the place where you think it would be very easy to have very separated telescopes and have a really a huge like dish.
Yes, yes. No, I think you're absolutely right. It's a very promising prospect, but technically it's still challenging. Let me put it this way: I think technically it's possible. It's just that yeah, it requires, I think, yeah, that people go for it and are motivated to build it.
Just if it's just a small cube, like satellite, do we really need a big, yeah, mirror, or is just something very small is sufficient?
Well, you could do with a smaller telescope. The thing is, then your collecting area is not very large, and one of the challenges in doing interferometry is that if you have very long baselines and very small telescopes, then the brightness of your object to still get some signal needs to be very high. So in those cases, you are often, you can only observe, let's say, masering or lasering sources that have a very high brightness temperature. The typical thermal objects, like we're talking about, have surface brightnesses of I don't know, for very cold objects 10 Kelvin, and for these disks you go maybe up to 1,000 Kelvin or so. But to have a very small collecting area, very large baseline, and still get a signal, you would need brightness temperatures that would be, of order of 10 to the 10 Kelvin or higher. So extremely non-thermal sources. So for astrochemistry, apart from measuring, let's say, masering molecules like OH or water, that would have a limited applicability. So I think you do need certain collecting area.
Okay, thank you. Yeah, there is one more question in chat regarding this discussion. Our discussion. LISA mission is based on interferometry and will be launched soon, right? It is for gravitational wave detection, but still, yeah. So I think that's just a mentioning about this.
Yeah, so yeah, LISA was just adopted by the European Space Agency. So LISA is a 3-element space interferometer, which will, because of its very accurate measurement of the length of the axis, is able to measure changes in space-time as these gravitational waves pass by. And this is done through, indeed, interference measurement. So the launch date of LISA, I think now is around 2034, 2035. So that still is 10 or 11 years away. And yeah, it's a collaboration with NASA, and NASA is a very important partner in that.
Okay, thank you, Rens. I think now our time is already coming to the end. So yeah, and I also don't see any further question here in the chat. So let's thank our lecturer once again for very beautiful and clear lecture. Thank you, Rens, very much.
It was a pleasure.
Yeah, and with this, I finish our today's lecture. Thank you, everybody. Good afternoon. Bye.